This is our last lesson in Chapter 9, and we're solving equations, inequations, and modeling. The ministry expectation here is to solve graphically and numerically equations and inequalities whose solutions are not accessible by standard algebraic techniques. So this is an important part here. What we're going to be working on today is not using the normal methods that we have for solving when we have a problem that can't be solved that way. For example, cos x equals x. If we're looking for the point of intersection there, we can't just solve that by saying, well, let's bring the x's to one side, or let's, divide both sides by cos or something. That's not a standard algebraic technique. So we have to come up with some other ways of solving. And one of them is graphically, like this one right here. We graph cos, we graph the line y equals x, and there's the point of intersection. Example 1, solve the following inequation by graphing. So here we've got a reciprocal and we've got an absolute value, and we have to find where one is less than the other. So we're going to graph each side separately. So let's break them apart. We're going to graph the left side and the right side. So that's the strategy we have to use here. There's no way we can take this and algebraically isolate x to find an answer. So we have to do each side separately. Let's start on the left. We've got, when we look at this equation, the 2 on the denominator tells us we're going to have a horizontal compression. Of course, we have a vertical asymptote at x equals 0. So we're going to have a vertical asymptote there. This number, if you recall from that unit, tells us we have a horizontal asymptote in that format that it's written. At -4. So we're dropping the parent graph is 1 over x, and we're taking that and we're dropping it down 4 units. So that's why we have a horizontal asymptote of 4. Our asymptotes will intersect at 0. Let me erase this here, at 0, -4. So our asymptotes will intersect at 0, -4. So let's go ahead and put our asymptotes on the graph. That's a little hard to see, but the asymptotes are both there and they intersect at 0, -4. So we've got our asymptotes on. Let's just get a few points that are close to kind of the center of the graph. Again, remember the parent graph, y-axis, x-axis. The parent graph looks like this. So it's going to look like that. It's in the same format with the 1 over 2x, means we're going to have a horizontal compression, and it's dropped down 4. So it's going to be very similar to this graph here. But we can just sub in to get a few points if we're not really completely comfortable with going ahead and graphing right there. So for example, if you sub in a 1 into the function, we're going to get 1 over 2 minus 4. So that's -3.5. So we can put that on 1 and -3.5. And you can do that and get a few more points. It's always good to get one in the other kind of quadrant there. Sub in a -1, that's going to be -4.5. -1, -4.5. So I know what it's going to look like because I know what the parent graph looks like. It's squeezed in a little bit because of that horizontal compression. So you can get more, you can sub in as many as you're comfortable with, but really you just want to get a few points correct. This is going to be -3.75, and that's really giving me a good enough idea of what's happening here. So I'm going to draw, I'm going to start I'm going to start up here really close to this asymptote, and I'm going to just gradually bring it down and curve it in a little bit and around, and that's good enough. And again, approaching the asymptote like that, and the same thing on the other side. So I'm going to curve around like that, and then coming up to the asymptote, and it's just going to continue on like that. So there is a sketch of our left side. Now we want to take a look at the right side. So the right side is an absolute value. I know it's got a vertex at -3, 2. I know it opens down because of that negative in front, opens down. And there's no stretch or compression because there's no A value or K value other than that -1. So all I really need to do is go over to my vertex at -3, +2. And since there's no stretches or compressions vertically or horizontally, I'm just going to go over 1 and down 1. And there's another dot. Whoops. And there's a point there. And again, over 1 and down 1 again. And so I can do that a few times on both sides. And I'm just going to have linear pieces. I'm going to get my ruler now and I'm going to draw lines and make an upside down V here. All right, so the question said solve by graphing, and we're looking for where the green one, this one, is less than the blue one, the absolute value. Where's the green one less than it? So we always start from the left, going from the left. Our points of intersection are very important. So here's a point of intersection right here. Are there other points of intersection? There are. There's one here, and there's another one. Now, I didn't draw these graphs to infinity, but will they cross again? So it's important to think about, because if I only draw a little V here, actually I started, you see how that's kind of a double line there? So I started there, and I was going here, and I realized, oh no, I have to keep drawing because I have to see where they cross. So I went back and I drew it longer because I need to see where they intersect. And they won't intersect again. These ones will not intersect again. So let's put some dots on where they do intersect because these points are going to be important. And your graph might be a little different from mine. Every time we solve an equation by graphing, we're really got a lot of potential for error. That's okay. So I've got 3 points of intersection there. I want to know where the green one is lower. So the first place I'm going to look is at here's my first point of intersection. Let's say that's at about, let's say that's an x value of negative, I don't know, negative 9.5. Okay, so on this, all the way to the left of negative 9.5, which one is lower, the green one or the blue one? Just in this section where I've done the yellow. So the one that is lower here is the blue. The blue one is lower than the green one. Does that match? Go back up and look at the question. Does that match what we have here? Is that what we're looking for? No, we're looking for where the green one, there's, let me just erase that. Let me put green here. I'm looking for where the green one, the reciprocal one, is less than the blue one. And that is not the case for the first section. So let's look at the second section. Second section is in between 9.5 and we have to be careful here. We don't go all the way to that other point, other intersection point. We actually have to go to the asymptote. So I'm going to go to where x equals 0. So looking down here, down there along the asymptote, which one is lower there, the blue or the green? And the green one is. So this section is good. We want to use this section between negative 9.5 and 0. That's going to be part of our solution. Now we have to look between the asymptote and our other point here. Let's say that's an x value of, let's say that's x equals 0.3 right there, right down there. So in the little space between 0 and 0.3, which graph is lower, green or blue? Between 0 and 0.3. The blue one is lower, so that's not part of our solution. That little part in here, in between 0 and 0.3, that is not going to be part of our solution. So let's look now between 0.3 and this point here. This point here, let's say that's x equals 2.8, something like that, 2.8. So in that section between 0.3 and 2.8, which one is lower, green or blue? Green is. So this is within our, this will be part of our solution answer. And now we go to the right of, I don't have any colors left. How about light blue, dark blue? Now I want to go from that 2.8 all the way to infinity. Which one is lower there in that group? So let's say we were looking at x equals 4. When x equals 4, let's go down. Here's the green one. Keep going. There's the blue one. So in this case, the blue is less than the green, and that's not what we're looking for. So this interval is out. So our final answer is going to be x is an element of, so we're going to write an interval notation. So our first segment we got was -9, and we're putting a round bracket, not a square bracket, because it's just less than. -9 to 0. That was the first piece where the green one was lower than or less than the blue one. And that is a union with from 0.3 to 2.5. So that is our solution of where the rational is less than the absolute value based on graphing. The next thing I'm going to show you is the solution on decimals. Here's what it's supposed to look like, but you can see our points of intersection were pretty close. This is actually, maybe more like a -9 here, and that's pretty close to a 0.3. I'm talking about x values here. They're always x values. And this here is, what did we have? We had 2.3. Yeah, this is pretty, it's about 2.5. So that's the solution anyway. And if you're using decimals, you can just click on the graph. This isn't a live graph. This is just an image of a graph right here. But you could click on the live graph and it would highlight these dots for you and get the actual answers. And you can always check these by subbing in a value. So if you want to see if an answer is right, let's say I sub in a -6, sub in a -6 to both equations. Once I sub it in, I should see that the value for my rational is less than the value for the absolute value, the answer for the absolute value. Example 2. Use a guess and improvement strategy to numerically determine 2 approximate solutions to the nearest 10. Here is our function. We've got 1. Instead of a function on both sides, we've just got a 1 on this side, but here we've got a cos with a x squared in there. So this is different than the normal cosine function we know. We just have to find 2 solutions, because think of the cos wave. It's going up and down and up and down and up and down, and it's going to have a y value of 1 many, many times. So we have a restricted domain when x is between 0 and 4, including 0 and 4. So let's start with the first endpoint, x equals 0. We're going to take x equals 0, we're going to sub that into the left side and the right side. The left side's a 1, easy. The right side is, this is the right side equation here. Put in a 0, and we get cos of 0, and cos of 0 is 1. So what we have here is we have found a solution already. X equals 0 is one solution, but there's going to be more in here. Remember, cos wave, it goes up and down over and over again, so we can get another solution, definitely another point of intersection. So let's try another number. So normally, if we were doing this in class, I would ask everybody, just get people to shout out numbers for me. So we'll try x equals 3. And we'll sub that in. Same process as before. The 3 is squared. That's 4.5. Cos of 4.5. Make sure your calculator is in radians. And we get -0.21. So we didn't get left side to equal right side. So that wasn't good. So let's try another one. X equals 2. Same setup at the beginning. Cos of 2 in radians is -0.41. Now, it's really hard to tell with sinusoidal functions, but it looks like we're going the wrong way, because we're looking for it to equal 1. This side does not equal 1, but it's closer to 1 than this one is. So again, sinusoidals they're going up and down, right? They're oscillating. So I don't really know, but I think maybe this one was closer. So that's what I mean by guess and improvement. So I'm not just going to keep guessing random numbers until I get close. I want to use the answers I have here. This is closer to 1 than this. So you would try another number here. And I will let you do this on your own, but the next one maybe you would try might be 3.4, right? Instead of 2.5, you might going in the other direction. So 3.5. And if you do continue on, I will show you actually the graph, but the next solution that you would find, I think, is 3.545. So that's something you can continue to try on your own. That's what the guess and improvement means. Because again, we can't solve this algebraically, so we need another strategy. Let's take a look of what this would look like on Desmos. This is the graph here. So here is y equals 1. That's my left side. That's the 1. And here's my right side. This is cos 0.5x squared. So it definitely looks sinusoidal, but it's changing, right? It's changing, doesn't have a constant period. It's much wider. One cycle is wider here for sure than it is out here. Between 0 and 4, you can see that we have a y value of 1 twice, right there, which is about your 3.5 answer, and right there. Our last example comes from your textbook, but I put the question right here. It says the population of Canada is measured on a regular basis by taking a census. So before we go on, what is a census? I just put a picture here of a really old census when it used to be taken by hand. A census takes place every 5 years. It's administered by Statistics Canada, and the data is used by the government to plan services and determine members of parliament. So it's how many people are in your household. It'll ask you all kinds of questions. What's the income, or all kinds of things about age and all schooling. So here's population from information from 1851 to 1951. That's what we're seeing here. They've got a 10-year period, 10 years, 10 years, 10 years, 10-year intervals. From 1951 to 2006, though, so the period, this column continues right here, 1951, 1951, but then they go to 5-year intervals in 1951, so it changes a little bit. The data in an XY table would look like what? So if I took this data and I needed to, because this is all about graphing, how am I going to graph all of this stuff? So to graph by hand, you would create a scatter plot and you would try to find an equation which would match the data. First of all, we need X values and we need Y values. In Desmos, you can enter your own table of data, and I will show you that I've already done that for you. But what's important to notice when you're reading these word problems, these are intervals of 10 and these are intervals of 5. So when you're doing your chart, my X value, the first thing I would have, let me write this down. My X value here, I would have an X, oops, let's make that kind of straight if I can. My X value, so my times 0 here, I'm not going to write 1851 to 1861 in the X value. That's this. This is my times 0, and then after that I would go to 10 because 10 years later, and 20, and so on. And I would do that all the way up. So these are all 10-year intervals all the way down here. Then I get to 90, and then it switches up here. This would become a 95, and then a 100, a 105, and so on. So make a table. This first number is 3,230, and that is in thousands, right? 3,230. And then you're going to just continue adding in these Y values here that you see in the table. They go down in your Y values. So the first thing you need to do in order to graph this is to get a good X and Y table going so that you can turn it into a scatter plot. So take a minute and just finish that table, fill it out, and then when you come back, we will talk about I will show it in Desmos, and then we will come up with a model, and we're going to use trial and error and matches this data. We're going to do a polynomial and an exponential. So first I want you to press pause and finish the table. So here is the table that I have put in Desmos. All of the numbers there, you can check them and make sure you got the same ones. We have to come up with a polynomial and an exponential. So a polynomial means we could do a quadratic, we could do a cubic, we could do a quartic, we could do anything that we learned in chapter 3. The easiest one maybe would be a quadratic. It could be quadratic. It does look like the data is kind of starting to level off there. You can almost go with cubic too. All right, see if I kind of trying to turn it into a cubic function maybe. It's just that this seems to be curving in the wrong direction there. So let's go with a quadratic. If I went with a quadratic, I'm going to try to hit some of these points here. Okay, that's not great, but what you would be doing on Desmos, if I had a live Desmos screen here, I would type in a bunch of A values and try to, let's move that out, it should be a little wider than that. Ignore this piece here. I would try to get an A value that works. So polynomial, let's say this is our vertex, we're going to use quadratic. So the vertex, we would write y equals a x minus, and that would be a 0 squared, plus, and that number is right here, 3,230. Now to find the a value, I'm going to sub in a point that I hit, or a point that at least looks like it's reasonable. So let me erase my curve here. I wouldn't sub in, let's say, this one here, because my parabola, the data doesn't really fit smoothly with that one, and I wouldn't fit the one next to it either, because if I do, I'll probably get an a value that's going to be too steep. So let's just pick a number in the middle here and sub that in for x and y. On the table, I'm going to circle that on the table, that's right here. So sub in 100 for x, sub in 16,081 for y, and we get 16,081 equals ax squared, whoops, not x. Our x is 100 squared plus 3,230. First thing you're going to do is subtract 3,230 from both sides to bring it over. You'll get 12,851 equals, and 100 times 100. Okay. And isolating a, we get a equals 1.2851. So the model I have for polynomial for this one would be y equals, and I could change my variables to match the question. I wasn't given any variables in the question, so I could use p at x there, or p at t for p at time, population at time, equals 1.2851 x squared, well, let's make it a t squared, plus 3,230. So there's a possible polynomial if we went with the quadratic. Now we're going to do an exponential. So this is good review for you. Exponential. Remember that when your x values aren't all increasing evenly, so these are increasing by 10s, but these are increasing by 5s, we have to use this formula for our base. What you need to do now is at least twice pick some coordinates, pick a few pairs of coordinates, sub them in here, get a b value, do it again, take another pair, get a b value, and then average them together. So again, if I was in class, I would give these out to a whole bunch of students, everybody would do a whole bunch of pairs, we would get all kinds of b values, and then we would look at the one that occurred most frequently, or we would average them together. So I would encourage you to do that a few times. But I'm going to go ahead and tell you what you might get. You might get a value of, for b, when you do it a few times, of 1.016 or something like that, approximately. Move that over. 1.016. So we get a b value once you do calculate your b value or your base at least twice. Then we need to put it into the equation. So that'll go in for b. What are we going to put in for a? Well, a is our starting value, our initial value. So this is our a value right here. And then again, you can go into Desmos and you can type this equation in and see if it's going to fit the data, because that's really what we're all about here, is trying to make it match the data that we were given. 3,230. Move that over. The base is 1.016 to the power of x or t. I used t before, so let me use t again, whatever variable you're using there. So that's two different equations for the same amount of data. And there are multiple ways you could have done it. You could have gone with a cubic, but if the textbook tells you specifically what types of functions to use, then I want you to try those. So that is it. That's the last lesson. That's it. And it's just a recap really of a lot of things that we've done already, but it's helping us to find equations that are inaccessible with our regular methods. So we're putting different functions together and we're trying to work with them, even though it might be different than some of the other methods we've done. That is it, and that's the end.